So, we have looked at this, the way that we address constraint processing is that you can pose problems as CSP or constraint satisfaction problems, and then you can use a solver to solve the CSP. So, the problems that can be posed in CSP, some of them are SAT, for example, is a special case of a constraint satisfaction problem, where each domain has a value only of true or false, and the constraints are the logical constraints of implication and or not and so on and so forth. Map coloring, we have already seen, can be naturally posed as a constraint satisfaction problem. The planning community has also posed planning as a constraint satisfaction problem, including the fact that the planning graph that graph plan produces can be seen as a CSP essentially. And there is also this planner called SAT plan, which converts the planning problem into a SAT problem, which of course is a special case of a constraint satisfaction problem. Consistency based diagnosis we have just seen can be posed as a constraint satisfaction problem. Then there can be problems of scheduling and many others essentially. So, the overall scheme of things that is appearing is that you have a problem and the user poses it as a CSP, and then you take an off the shelf solver from somewhere, and that produces the solution for us essentially. So, now we want to look at how to solve CSPs. We have already seen that the process of using constraint solvers is that somebody which is a user takes a problem and converts it into a CSP, which is an input to the solver, and the solver produces a solution. So, let us look at some of the algorithms that are used by solvers of constraint satisfaction problems. So, here is some terminology that is often used in constraint satisfaction. We will discuss it a little bit informally, but hopefully one will get an idea. We will use A for assignment, and we say that an assignment AZ assigns values to a subset Z of the variables. So, set of variables is X, a subset of that is Z, and if you give values to those variables, then we have an assignment essentially. So, an assignment is a tuple of values which will stand for values of the subset of variables that we have selected essentially. Very often we use A for an assignment, and we could use something like this, reading from right to left, as you can see, is A1, A2 up to AZ minus 1 up to AZ. So, assuming that we have taken these Z variables, assign a value to the first one, to the second one, and so on and so on. So, the fact that we have written in this reverse order is simply because of the fact that the last one to be added was probably the Zth variable, and to be consistent with how the algorithm would represent it, we have just represented it like that. So, let these be the Z values. So, remember that assignments are values. So, A1 is a value, AZ minus 1 is a value, A1 is a value of the first variable in this set subset Z, and AZ is the value of the last variable in the subset Z essentially. So, it is a tuple. Now, we project this tuple, that means we select a subset from that and we call it A of S. So, let it be a projection of this assignment on the set of variables S, then we say that if S happens to be the scope of this particular relation R, then we say that AZ satisfies the constraint C. What is the constraint C? The constraint C has a scope S, which is a subset of X, and R, which is a constraint or the relation between those the variables, which is the subset. We say that an assignment AZ that we have drawn on the top, this is a tuple of values, satisfies a constraint if S is a subset of that Z to which we have given values, and the tuple AS. What is the tuple AS? The tuple AS is from this tuple A, we only keep those variables who belong to the scope of the relation. If that tuple belongs to the relation, remember this R is the relation which is the constraint, specific constraint C that we are talking about, then we say that an assignment AZ satisfies a constraint C essentially. So, just to repeat, an assignment AZ, which is a set of Z values for Z variables, satisfies a constraint C, and the C is on a subset S of variables. If that subset S is a subset of Z, which means we have values for all the variables in the scope S, and we have such values that the constraint C, which is represented by a relation R, is satisfied essentially. So, an assignment can satisfy a constraint essentially. We say that an assignment AZ by itself is consistent if for every constraint of this kind, remember that a constraint has a scope and a relation with it, such that the scope is a subset of this Z that for which we have an assignment. For every such constraints, AZ satisfies that constraint, then we say that AZ is consistent, which means it satisfies every constraint that it covers essentially. A solution of a CSP is a consistent assignment for all the variables of X essentially, which means it must satisfy all the constraints which are there in the CSP. So, now let us talk about the search algorithm for solving a CSP essentially. So, let X is equal to x1, x2 and xn be the order in which those n variables will be tried essentially. So, let us say we are fixing the order. This is different from the algorithm we had very briefly mentioned earlier, which was dynamic variable ordering, where we chose the variables based on certain criteria, which was the size of the domains. But for the moment, here let us assume that this is fixed essentially, that you will look at x1 first, then x2, then xn, and for each variable ai or for each variable xi, it has a domain di which has the values ai1, ai2 up to whatever the number of values are, and they will be tried in this particular order. That let us say we are looking at x1, then first we will try a11, then we will try a12, then we will try a13 in a particular order essentially. The algorithm backtracking, which is quite well known, is as follows, that for each variable xi, try the values in its domain one by one till a value which is consistent with the earlier variables is found essentially. If a consistent value is found for this variable xi, then we advance to the next variable xi plus 1. If a consistent value cannot be found for this variable xi, then we go back to xi minus 1. So, we do this starting with I is equal to 1 to last essentially. If you can find a value for that variable xi which is consistent with the previous values, then we go ahead to the next. Otherwise, we go back and try a different value for the previous variable which is xi minus 1. So, termination can happen in two ways, is that we have exhausted all values of x1. So, we have backtracked to x1, tried all values, and we can't find a value which will work. So, we do not have a solution. The other case is that when the last variable, when we have moved to the last variable, if there are n variables, remember that the number of variable is x1 to xn. When the last variable we can assign a value, that means we have assigned a value to all the variables and we have a solution. So, this is the algorithm backtracking. It takes a constraint satisfaction problem as an input, x, the variables, the domains and the constraints. It initializes the assignment to an empty list. So far no values have been assigned. It says I am going to look at the first variable I is equal to 1, and it makes a copy of the domain. Essentially, it will work only with the temporary copy of the domain, so that it does not destroy values from the original domain. Then it started with I is equal to 1 and it will progress towards n, and for each value of I it will call a function called select value, to which it will give a copy of the domain, this di prime that it has made, along with the assignment that has been constructed so far. Initially, of course, the assignment is empty, as we have seen here, and the constraints that have to be satisfied essentially. So, what does this select value function do? It takes out elements from this di prime, which is a copy of the domain for the ith variable, one by one, and we have already said in the order from left to right. So, it extracts the first value from the domain of I, and then it updates di to the tail. If it is consistent, we have already defined this notion of a consistent, and assignment is consistent if it satisfies all the constraints whose scope fall within the variables that this assignment has given value to. So, A is what we had passed to this stage, we have constructed till I minus 1, and A I is the value that we are choosing for this particular variable essentially. So, A I is the next value for the ith variable that we are selecting. If this assignment, that A I concatenated with the earlier partial assignment, is consistent, then we can say we have got a value and we return this A I essentially. If we have tried all the values and di prime becomes empty, that means we can't find a value for that and we return null. So, this select value function will either return a value ai, and that should be the value for the ith variable, or it will say I can't find a value for this ith variable. So, then we just look at that. If ai is null, that means we couldn't find a value. So, we go back to the previous variable I minus 1, and we remove the last value that we had selected for a, and so we just keep the rest of the values and say this is the assignment. We are going to look for a new value for a I minus 1, for x I minus 1. If we have found if it is not null, that means it is given us some value, then we augment the assignment by saying we put a I at the head of that assignment, increment I is equal to I plus 1, and if the new I is less than or equal to n, we make a copy of this its domain and go into the while loop again essentially. So, remember that this assignment A, we started off as an empty assignment in the first line of the program, and then we augmented it in the line number 9 of the program whenever we found a new value. If we could not find a value at any level, we went back to the previous level, and in the line number 8, we removed the first assignment and kept only the tail of the assignment. So, either ways, when we exit from this thing, we have said that there are two ways you can exit. One is that I becomes less than 1, or the other is I becomes more than 1 essentially. So, in one place we are decrementing I, in another place we are incrementing I, and the while loop says that as long as I is between 1 and n, you do whatever we are doing here. If it becomes less than 1, that assignment would naturally have become empty and we would return that empty. Even if it has become more than n, we would have found a solution and we would return that solution here. We would only reverse it just to say that this is the first variable, second variable, and so on. It was constructed in the reverse order. So, here is this map coloring problem, another map coloring problem. So, we have these regions A, B, C, D, E, F, G, and we have some domains for each of them as shown here. So, I have not written the names here, but this is A, this is B, this is C, and so on. You can see in the diagram on the left. Each of them has a domain of some values, and we have selected the order in which we are going to process them, and the order is G, D, B, F, E, A, C. Somehow we have chosen this order. So, this is G, and that is the first value that we will look for. So, this is the order that we are working in, right, G, D, B, F, E, A, C, and the algorithm will search through all possible ways. It is basically a depth first search algorithm. As you can see, it looks at the variable G to start with. What does the variable G has? It has 3 values W, R and B. Then it will go to variable D, which is the second variable. It has a value G, B, M. And this is what this tree is also showing. It starts with a variable value W for G, then it tries a value G for D and so on. It basically goes on, it will search this entire tree and figure out that this part of the tree does not give us a solution, and then it will go with the new value for the variable G, R, and eventually find this solution which is here. So, this is the tree that is explored by algorithm backtracking, which is basically depth first search. When it finds the first solution, there may be another solution which is on the right side of the tree, but this is what we have seen. Now, we have mentioned that one of the main things we are doing when we are searching for solution is to battling this monster that we have called as convex or combinatorial explosion, and there are various approaches to combat this exploding number of choices by choosing an appropriate ordering of the nodes. That is one approach that people who are working with constraints do, and one of the ways of doing that is to use what is called as a min induced width of ordering. So, there is something called min width ordering, which basically says that take the node with the highest number of edges coming out first, because that node would influence many other nodes. And so, you do what is a min induced width ordering, which is a variation on that, which says that every time you select 2 nodes, you connect their every time you select 2 values, you connect them, so that is also another edge essentially. So, the basic idea behind that is that you select the nodes with the highest degree first, so that they would influence the ones with the lower degree, and very often that is known to be work well essentially. But finding the min induced width ordering is not necessarily a simple task, it is more than polynomial in time. Then another way of ordering the variables. So, this first one is based on the graph structure, and a variable which is connected to many other variables should be considered first. The second one, and that we saw a glimpse of earlier, is the dynamic variable ordering, which says take that variable who has the smallest domain, which has the smallest domain, because that is where you are going to otherwise run into a problem. So, choose variables with the smallest domain first essentially. And another thing is to pre-process this entire network, so that we can prune the search space, and this is called consistency enforcement, that we will see soon essentially. A combination is to prune the domains during search, which means that while searching you look ahead, and we got a feel of that when we were doing the map coloring example, but we will come back to this again essentially. This is called look ahead search. And then there is something called intelligent backtracking, which is also called as look back search, which basically tries to figure out that if you have run into a dead end, where should you jump back essentially. So, these are kind of called intelligent backtracking these things. I had very briefly mentioned dependency directed backtracking when we were looking at AND or trees essentially. And another feature that we often use is memorization, is that you remember what combination of values can never be solved, and these are called no goods. So, store them in the memory as you are solving those problems. The next thing we will look at is consistency.